some motivation. Got it? Yeah. To motivate a bit, yeah, this you have to. The research perspective of why do we need robotic assistance apart from the daily tasks, these repetitive household tasks that we would like our robots to take over. I think there is a greater societal impact on other domains, for example, like in hospitals and in caregiving, where robots could take over and do all these repetitive, for example, pick and place, handover tasks that nursing and caregiving staff would not like to do, and they could even focus to more challenging tasks that robots may not be able to do and perform. So, and to continue on this direction, in Germany, in particular in Europe, that I am working, there was recently a documentary by Deutsche Welle, that it is one of the biggest broadcasters in Germany, where they noted during the pandemic a shortfall of 30,000 caregiving workers. And even the ones that are actually going and provide assistance to the elderly people, they are actually called ambulance workers. So they go, for example, for 1 hour, 2 hours, they give some medicine, they prepare some food, and then they leave. And then these people, they are saying that we feel abandoned by society. And I have to tell you that Germany is actually has a very, very good system in caregiving and everything. So imagine if Germany has a problem, what happens in other countries? So the vision of having personal robotic assistants is real. And in particular, if we go to the cases like pandemic where people were quarantined, we're going to understand how important this is. And these robotic assistants, we have seen them in Hollywood movies, in cartoons. We envision them being these human-like robots, being able to perceive objects and humans. They can learn to execute household tasks, and they can adapt to the human needs. But why don't we have such robots yet? So in the past, we didn't have the hardware and the algorithms, but I think that now things are different. Now we have better hardware. We have robots with anthropomorphic bodies and increased dexterity. We have the computational power to accelerate our algorithmic processes thanks to the faster CPUs and the cluster of GPUs. We have cheaper, faster, and more accurate sensors. And thanks to the deep learning revolution, we have also better perception algorithms. So what is still missing? I think there are missing many, many components, but in my research, the focus that my research mainly focuses, and the iRosa lab focuses, is on how we can enable mobile manipulator robots that I think they are emblematic example of such robots that can enter household environments, human inhabited environments. How can they learn skills, plan assistive tasks, and interact with humans safely? So I will not cover everything that I do in my research, but I will just focus the ones that have as target the human and learn from the human. So I will cover topics related to the human behavior understanding and prediction, adaptive human-robot interactions, given that we have encoded some behavior of the human, and then efficient skill learning from human demonstrations. So a large part of the things that I will talk about was part of my PhD studies. So during my PhD, I was working in a research program in Europe that aimed to develop this kind of robotic rollator. So this rollator aims to support people that they have mobility issues, and also to act proactively. So understand what is the pathological status of the gait of the human, understand instabilities, and therefore control the robot accordingly to provide optimal support, assistance, and also other rehabilitation scenarios that you will see in a while. Mainly, this thing was equipped with many sensors, but I mainly was working with the camera that was tracking the upper body and the laser sensor that was scanning the legs. And one of our goals was to develop a system that would understand the different gait phases. This is a gait. This represents the standard gait cycle of normal walking, and we wanted to encode the dynamics of these hidden states in order to understand the pathological also status of the human, because once you can do this kind of segmentation, then you can extract gait parameters that can allow you to classify the status of the pathological walking, and it is actually used a lot by rehabilitation experts. So one of the contributions here was an interacting multiple model particle filter that would take this Markov model that would encode the gait phase of both legs concurrently, and it would learn, we learned dynamics for each leg separately according to the gait phase. And then thanks to a probabilistic data association technique, we were able to track both legs without being, for example, obstructed by clutter, other people walking around and so on, and also only using a few particles. And importantly, we were able to couple it with a maximum a posteriori estimation such that we can always predict the next gait phase. And since you know the gait phase, you can basically drive the selection of the dynamics model to always adapt to the type of walking of the human, because actually the pathological walking has nothing to do with the standard gait phases of the normal walking, because more or less in humans, we have more or less the same rhythm in our walking. Now, if we couple this information from the performance of the legs regarding like the status of the legs and the status of the gait phases, and we also couple a tracking system for the upper body, we can then argue about the human stability. Now, for this system, we wanted to have an indicator of whether or not the human is near incidents of that were risky, risk of fall. In order to do this, we relied on motion capture system that we used with real patients. So the patients were wearing markers. We were recording their way of walking. And then we relied on biomechanical models in order to understand the type of walking. And there are specific metrics where you have to couple the center of mass with the base of support that is formed by the legs in order to classify whether or not you are near a risk of fall incident or not. Obviously, we didn't push the humans back then to fall down. So we trained an LSTM-based network that would take only information from camera and lasers, no wearable sensors to indicate whether or not there is a risk of fall. And this worked pretty well against other classification methods. And importantly, it was a non-wearable technique that can be used on the rollator as an indication of risk of fall events. But being able to predict human behavior over long horizons is very important, in particular when you want to plan assistive behaviors by robots. And we know that our robots are also a bit slow, so we need to ensure that we are able to plan to start the planning proactively, as I say. So I believe that having a whole body representation of the dynamics of the humans is very important, such that you can do long horizon motion prediction. And in this direction, we developed a directed acyclic graph neural network, where we, as you see on the top here, we represented the human skeleton as a directed acyclic graph. And then we did several operations of graph convolution operations and temporal updates in order to learn the internal dynamics, where we would also learn the dependencies of the limbs and the joints compared to what is commonly done in these processes. And then with a directed acyclic graph gated recurrent unit, we could predict into the future the evolution of the motion for the whole body. And this would give us some state-of-the-art results, in particular for most tasks on standard data sets that are used for motion prediction and activity classification. And what we also wanted to see is that, okay, we have a good motion prediction model. Can we couple it with an intention recognition module in the end, such that we can say, okay, I can predict in the future what you are going to do? Can I, how your motion will evolve, sorry. Can I also classify what is the action that you want to do, such that I start my robot, all the planning process. And indeed, we showed here that if you take our method and couple it with an intention recognition module, due to the fact that we encode better the dynamics, it's also easier to classify better the intention, and then we would trigger this now robot there to interact. And if people have ever worked with now, they know how slow it is. So starting planning early, the action that the now has to do is important. Now, intention understanding is Obviously, you can get information from posture, from actions, for example, gesture recognition, action recognition. You can get pretty good results. However, we cannot forget about language. And in this system, we basically coupled all the technologies that we have developed for this mobility assistant, where we would have human activity recognition with gesture recognition, exercise monitoring. We had a microphone array where we were doing natural language understanding, and then we were doing some kind of late fusion between the gesture recognition and the or posture activity recognition with the natural language to understand the human intention in the end. And of course, okay, we also had, when there was walking involved, also the gait analysis part would take place. I will give you only one short video for time interest. Here, the human is doing some rehabilitation exercises, and we would give also the score of the rehabilitation exercise as a way of understanding whether or not they are performing the exercise correctly. So we knew what exercise they had to do. Or the system will ask them to execute, for example, the exercise up to a maximum number. So as I said before, it's important to couple our motion prediction models with actions for our robots. And in the case of the mobility assistant, we wanted to be able to adapt the formation of this robot to the way the human was behaving. And this was a pretty challenging scenario because the robot was always in the front. It would capture the information backwards about the human, and it should always adapt to the human in this front following navigation scenario. So what did we do? We relied on this multimodal human-centered tracking, where we will take the upper body, capture the center of mass, have the laser, and have a coupled ascended Kalman filter-based tracking mechanism to have a reliable tracking of the human. We would train a human intention model to see where the human wants to go, to predict where the human wants to go. And then if we take this information about the intention of the human together with the current position of the robot, or the state of the robot, actually, not only the position, we can train an interaction model that can encode these dynamics that are very difficult to encode in this scenario of this front-following navigation scenario. Now, if we have this interaction model that actually gives you the deltas of the change in the velocity of the robot, you can shoot them in a model predictive control, find the optimal action given some coupling parameters that we can estimate online that can be dependent on the stride length of the human, etc. This we have worked together with medical experts in order to specify these things. And you can adapt the action of the robot, collect the data, and after several data collection, you improve your model, and you do this again and again in a model-based reinforcement learning fashion. And we have done some evaluation scenarios. Obviously, we didn't have enough humans to operate on, so we did a lot of things in simulation. Also because all our data are from real patients, and this, as you may understand, requires a lot of also legal procedures to bring patients into our lab. But what we have found out is that if we did plain imitation learning, we get the worst results. MPC with a kinematic model was quite good. A kinematic controller that relied only of leader-follower standard literature was the worst, but the model-based reinforcement learning that learned the dynamics of this interaction was the best. And I think that this is an interesting result also for follow-up interactions with humans, the fact that you have to learn this interaction dynamics. And here you can see another scenario again on my, we are still on the project of my PhD. Then I switched, it was a long PhD, I will tell you another time. Then we moved to another project where we were developing projects to assist, so that we call it infotainment technologies, to assist typically developed and autistic children with autistic, that belong to the autistic spectrum. The goal of this experiment that I will explain now was to engage the child in a joint attention task. So the goal was to create some experimentation, some scenarios where we could help autistic children develop their social skills, that it's something very, very difficult. And usually these children do not want verbal interactions. They prefer mostly motor skills. At least in this scenario, what we wanted to study was in particular the case where you have a child and a robot. You can track the child from multiple cameras that we had in the room. We also extracted several features that would encode, for example, the gaze of the child with respect to the robot and the object in the scene. And we would train a neural network that would classify the engagement of the child in the task. The labels for the engagement classification were provided by psychologists that they were working with us in this project in some manipulation scenarios that we have done before we trained our data, so with data collection. Now, what we can do with this engagement signal, we can train a reinforcement learning agent that would learn how to adapt the actions of the robot, and the actions of the robot were only motor actions, such that pointing, turning to look at you. How many times should I turn to look at you? What is the intensity of this motion, such that it conveys to the child the intention of, oh, I need you to hand me over this object. And the goal was basically this, that the children show this, how do we call it? No, the intention of like providing assistance to a robot. And we have seen that for most kids where their spectrum was not, let's say, severe cases, it really helped over like the response times was much faster than the hard-coded controller that we had. So this adaptation with respect to the engagement was good, but I would say having this discrete signal was not always good. So we had to parameterize it in the end and give always a continuous like time-weighted signal from this discrete classification that we were doing. But obviously, if you want to interact with humans, and now if we go to the home environment or the hospitals, you care about safety. It's not only about understanding the behavior of the humans or predicting the behavior of the humans. Now, in this work that was just accepted at IROS, we took the idea of training sign distance fields, and we wanted to train these sign distance fields from such that they can predict distances at any point. So wherever you are, you can measure your distance with respect to the surface of a human, of the objects around you, and so on. And then we can use these sign distance fields in safe planning or safe reinforcement learning, as I will show you in a while. So our method is pretty simple. It builds upon the deep SDF paper that basically learns to the SDF, the reconstruction of the surface of objects. And we trained it for articulated objects like humans and robots and everything that we had that are relevant to our tasks. So the main idea here is that you have a position of a 3D point that you want to evaluate where it belongs. And then you have a pose that can be, for example, in the case of the human, the skeleton information of the pose of the human. You pass it through a network that basically learns this distance field. I will not go through the details of the math. And it additionally makes the following assumption. It makes the assumption that when I am not close to the body of the human, there is a Euclidean metric representing my distance to the human. Therefore, I consider that the human or the object in general is a point mass, and I can represent the distance field as a Euclidean ball. And we added this regularization term. So basically decide when you are a unit, a point mass, or where you are like this complex high dimensional surface. And it was self-supervised by the network itself, whether or not I have to take a detailed information on the manifold or not. These are the methods that we compared against: the ECOMAN, the DeepSDF approach, and the RedSDF. It's our approach, and as you can see, the fields that we create are actually in very large distances quite, how can I say, normal, because they are Euclidean, while here we have again distance fields, but they are quite distorted. And we have more results in the paper. And here you can see an example where we are just sampling distances as the robot is approaching the human to perform theoretically a handover. And you can see that the moment that you go very close to the human, you have to have a very tight, for example, bound on the surface of the human, such that you can perform the handover without hitting the surface, the safe space, let's say, of the human. And we can, oops, this one doesn't play automatically. Yeah, and we can also do this the same thing for the robot. So we trained the deep SDF of our robot, and we used it for reactive motion, whole body motion generation, and we compared it against a sphere-based, that it is a classical approach for doing obstacle avoidance, while we have a neural network that we can query for hundreds of points, and we see that we have much smoother control. And this is just an artificial potential field, like the standard Osama-Khatib approaches. Yeah, and we can also apply the same method. Again, this is a very simple reactive controller where we have like a always sampling a distance field at 0.1 meters. It could be whatever you want. And the goal here is to go to these waypoints while avoiding collisions with the humans, where we have recorded already human behaviors, and with a bit of effort and engineering, we put them inside PyBullet in order to have these more realistic motions of humans for training agents. Because our goal is to do safe planning and safe reinforcement learning, and now this is a work in progress. We are using these manifolds that we can reconstruct as a way to learn basically differentiable constraints in order to do safe reinforcement learning, where here, for example, the goal was for the robot to deliver the mag to the desired location while avoiding the human and not colliding with the table, so many constraints. And we basically constrain the exploration space. So we constrain the action space here of where you should take your next action in these particular experiments. So there are specific tasks, like imagine that you have your robot, it comes to your house, it has a specific skill set, but there will be also skills that you may need to teach your robot. So for this case, for non-expert users, learning from demonstration is a very effective way to transfer new skills to robots. And in particular, when you cannot have an accurate world model and you have like limited task specification, learning from demonstration is a very, very good framework. However, usually this methods do not generalize, and you usually, when you train a policy and then you put it into the real world, you need to keep optimizing this policy. So there are many different ways for doing imitation learning. We like the option of movement primitives. So you have these parameterized skills that have learn a distribution of parameters and context over some demonstrated trajectories. The good thing about this thing is that you only need to provide a few trajectories, but usually because this is high dimensional, so you are always operating in the joint space, and maybe there is the context that it is, for example, some obstacle or whatever else in your task can be in another space. It's somewhat complex to do policy optimization, so keep improving these methods. So in this work, what we did, we mapped it with like classical machine learning. We mapped it into a reduced latent space using mixture of probabilistic principal component analyzers. So imagine that you have now a reduced latent space over the movement parameters and the context, and it is multimodal because you have the mixtures. And this gives you a very nice closed form solution in which you can do basically policy optimization over it. And for this, you can do off-policy reinforcement learning with important sampling, because you keep reusing also the demonstrations that you have, and you now have new data that you collect during the new experiments that you do. And you can also regularize it such that you don't forget very fast your imitation learned policy, and you can have like a context regularization. And this it depends on the task that you are solving, what is the context that you have. I will only show you here the pooring task that I find really interesting. This red, I don't know if you can see. So this is from 100 demonstration of kinesthetic teaching, the pooring task. We can measure automatically here the poured quantity. But I don't know if you can see that the robot basically learned to do this motion, but the actual obtained poured quantity is not actually accurate. Here, for example, we wanted 128, it poured only 16 grams. So what we can do only with 9 new interactions, so 9 more episodes, where we can use this signal as our reward function. We optimize our policy and we can actually obtain pretty good results. So you see here, there was a deviation of 6 grams, here a deviation of 2 grams. So the robot very, very fast obtained new experience, updated the previous policy from kinesthetic teaching. But again, I would say that doing kinesthetic teaching is not always the safe way that you would like your non-expert users to provide information and new skills to the robot. So what we are currently also researching is a way to do imitation learning from videos, from visual information. And whoever works with pose estimators, you know that they are very bad in real life, in particular, like with different conditions of lighting, different cameras, and so on. So what we started doing is researching ways of extracting unsupervised key points that are very consistent across time. And these are results of our method, and these are the results of the state-of-the-art methods. And the difference of our method compared to the other approaches is that we rely on information maximization for detecting the key points. And this means that what we do is that we supervise all this process of extracting key points only by caring about the entropy of the image. So the entropy in the image is the information that we need to represent by our key points. We need to maximize this information. And we consider that these key points are the carriers of the important information. And in order to do also tracking, we need to have some kind of consistency transportation of the information. So inspired by the transporter networks, we are transporting the information around the various key points to new video frames, such that we can always constrain that the key points should represent the same amount of information. And we don't rely on any reconstruction. So there is no elbow, for example, here for reconstructed images, that it is pretty common in key point detection, and usually it gives pretty weird results. This is a very difficult data set. It's called the SIMITATE data set. What is good about our method is that we can detect both static and dynamic objects in the scene, at least without any model or anything about the environment. And the other interesting thing of our approach is that we can activate key points once new information is available. So we don't have just key points lying around. The key points appear whenever new information comes, and then it will disappear whenever this information goes. Obviously, it's not optimal yet, but we are keep working on it, trying to impose some kind of structure on the key points. But we are very, very excited about these kind of approaches for transferring demonstrations to robots from videos. So the main takeaways of what have I talked about? I talked about some bits of human behavior understanding and human prediction, but I think that we need longer prediction horizons, and I believe that it is very important to have some sort of semantic coupling already, so some kind of semantic geometric coupling of the information when you want to do contextualized motion prediction. Still, we are very, very slow in, like, we need to be able to push this behavior prediction further if you want to engage in long horizon also interactions with humans. I talked about learning skills from demonstrations. One big challenge is the mapping from the human actions to the robot actions. We have different degrees of freedom. We have different, for example, task spaces, workspaces. So how do we do this mapping? And next, how do we handle this large offline data that we can get from videos and so on? There was a workshop on Monday that they talked also about all these things. And we also talked about adaptive human-robot interactions. And I believe that key aspects right now is safety, not only safety, but also trust between human and robot. How can we measure it? How can we have some signal like the engagement that we can track and, for example, make our robots adapt their behavior so that they can be more compliant to humans. And we should not forget about human feedback in various ways. It can be signals, it can be language, and this is something, for example, that I have not added into my work, and I think that it is very, very important. So yeah, I would like to thank my students and my collaborators, and yeah, thank you for your attention, and I'm happy to take questions.
Hi, very great talk. Thanks so much. I'm wondering on the first part, the like human behavior modeling. I imagine that when you put a robot in it, the behavior of the human will change. And I was wondering, what are your thoughts on this? Like, should we be training these behavior models with robots in them, or how do we account for by these behavior changes?
So this is a very great question, actually. This is something that we are also thinking a lot. Usually what we do, in particular, if you have dyadic interactions, is that you have human-human interactions and then you try to transfer them. But then, yeah, as you said, when there is a robot, maybe the human behaves completely differently. I think of having some kind of safe policy optimization there so that you can adapt and personalize to different people, it's important. But one other thing that I am very, I would like, for example, to join together and like do something for this direction is to create some kind of simulation environments with humans, but when the humans coded in a similar fashion, for example, more realistic motions. But then we come again to the point that in, for example, the example that I showed with safety, right? Here, the human is agnostic of the robot. It's just demonstrations that we recorded before and we transferred them into PyBullet so that we can have more realistic example. I would expect that the human, while interacting with the robot, it will adapt also a bit to the robot. So it's a question. And I think that this goes to the trust part. How do you measure the compliance of the human to the robot? And how can you, for example, online adapt? I don't think you can have a robot that you say, I have the skill set, it operates so well in our benchmarks, we put them into the real environment and then that's it.
Thanks again for your talk and also for your talk on Monday. I have a question about the project where in your PhD where you were working with autistic kids. You tried to learn a predictive model of engagement. And these are this by itself is not just like a challenging task, but you're also working with some pretty challenging subjects. I was wondering what you found about the model was sort of predicting correlated highly with engagement, and whether like learning these sort of predictive models of a very high level like behavior is something we should be doing.
So definitely the thing that helped a lot into, first of all, we should understand that there was also some kind of subjective evaluation by the psychologists that they just scored interactions as, you know, engaged, disengaged or not. So already we had a lot of variability there. Then when we go to the modeling part, at least in the way that we have structured the network back then, maybe now if I will do it, I would do a different kind of model, not an LSTM-based model, but most likely a graph neural network-based model that would take also the robot more actively into account. But in this case, encoding by ourselves features like the gaze, the for example, the orientation of the head with respect to some center of mass was helping a lot into the prediction. So we already have encoded this. But I would say that right now, if I had to do it, I would do it differently. Yeah, back then we didn't know graph neural networks. I don't know if this was like something that you asked, or did I?
Direction. I guess one follow-up question is that when you were evaluating this model, what kind of accuracy? I don't know if you had enough even data to kind of test set or eval set.
I mean, we had. I don't remember now exactly, but I remember that we have like 20 kids in the test set. So we like did the standard 20, 80%, and then we evaluated against some SVM random forest approaches. This was much superior. And then the evaluation was in the follow-up, the other type of evaluation, let's say. And then let's say, I have to maybe clarify, this was already on data that we have gathered, and we just treated it as offline data where we did train and testing. With the kids, then we had a second evaluation where we tested the reinforcement learning approach. So we weren't evaluating there on the fly whether or not our engagement was good or not. Exactly, we made the assumption that we had this, and we were testing basically the reinforcement learning versus a hard-coded scheme. Basically, it was an operator that would push now point and now do this, so that you can have some kind of also randomness in the way that you would treat every child. Yeah.
I remember you also said that, like, I'm sorry, oh, sorry, but
we can discuss it. Yeah. Yeah.
Thank you.
Thank you so much. Yeah. Thank you very much.
So I will introduce our second speaker in the afternoon. Julian DeFurters. So Julian is an assistant professor of business administration in the marketing unit and the director of ethical intelligence lab at Harvard Business School. He grew up in South Africa and earned his BA from Yale, his master from Oxford, and his PhD from Harvard. He has also held research positions at Stanford MP, so many different places. So Julian is a cognitive scientist who conducts research on ethical intelligence as an intersection of psychology, ethics, and AI. He has published more than 20 articles in leading journals and won multiple prizes. So today he's going to talk about the stigma against AI companions. So if I guess correctly, it's going to be about the opposite direction compared to, I guess, Georgia's talk. So Georgia's talk will be about robots understand human, I guess. He will talk about how we can perceive AI. So please welcome Julian.
Thanks, Tianmin. Can you all hear me there?
We can hear you.
Great, okay. Well, thanks so much for you and Sherry and the other organizers for putting this together. I've really been enjoying all the talks and feel fortunate to be a part of this. I am the head of the Ethical Intelligence Lab at Harvard Business School. We are in a marketing unit, so we study how the moral psychology of consumers colors their attitudes toward firms and the new technologies that they put out, and how firms can market in ways that are sensitive to these moral buttons in turn. So this is obviously a big area, and so we study it through specific case studies like autonomous vehicles, something called brand activism, and what I'll be talking about today, AI companion applications. All right, so have you been feeling lonely of late? Well, if you're like 3 out of 5 Americans, you may have answered yes. And when you think of this from a sort of market opportunity, this is really a huge business opportunity for folks who are building technologies that will diffuse readily and satisfy consumer needs. And in fact, some have estimated that loneliness is even on the rise, leading some to call it a so-called loneliness pandemic, which no doubt the recent years of social isolation and political division have not helped with. And we also know that loneliness is linked to various deleterious mental and physical health conditions. And it's costly, estimated at around $2,000 per person over the course of 10 years, mostly in the form of hospital admission costs, or as high as $7,500 for those who are especially lonely. So it appears then, as a society, we're not doing very well at addressing this societal problem. And so what other potential solutions might exist? Well, in the movie Her, there's this idea that, in the near future, we might be able to solve this problem in part through AI companions who do not simply perform a specific task for you, but can engage in free-form conversation of a friendly or even romantic variety. Now, the director, Spike Jonze, was envisioning a near future, but he may as well have been talking about the present because such applications are now here. If you simply pick up your phone, you too can have an AI companion. And the relative advantages of these kinds of applications compared to applications that connect you with other humans are obvious. So it's cheaper. For many of these, there's a freemium version that you can enjoy another companion without needing to pay for the premium features. As these apps advertise, the companion is always available to listen and talk to you, and it's always on your side. So unlike a human that might judge you, the responses of these applications are generally quite validating. You might be wondering whether this is just a sort of niche thing, but actually some of these apps like Replica, for instance, have around 1 million monthly active users, and some folks who have had relationships for as long as 2 to 3 years with their AI companion. And as in the Spike Jonze film, there are also romantic options available. So it appears then that we have a great product to answer the problem that we started with. Yet a classic lesson from marketing is that new products do not necessarily sell themselves, even if they're great products. So of course, this is a bit of a sad realization if you've gone through all the hard work of engineering a new product, let's say one in this case, that has aspects of social intelligence. As an example of this, in the MBA curriculum at Harvard Business School, we teach about a product called Apex ski boots, which solves the problem of bloody toes. Apex ski boots do not give you bloody toes because they're not hard. They have a soft boot that slots into a hard casing, and it's the casing or the cage that slots into your ski. Yet for various reasons that I won't get into, Apex ski boots have not taken off in the way that its makers envisioned. And more broadly, we know that there could be various reasons that a great product will not actually deliver on its promises. It could be incompatible with the existing way that consumers do things, could be difficult to understand, hard to try out, and you might not even notice it in the first place. And so for these reasons, it's important not just to strive toward engineering great products, but also understanding how consumers perceive them, especially when they're new, as in the case of an AI-based product. If you do this, then you can anticipate how the offering will be received. You can proactively tweak it so that it will diffuse into the market more readily, and you can tailor your market fits to overcome any potential barriers to adoption. So with this in mind, what we wanted to know is whether engineering a great AI companion is enough to deliver on this promise of AI companionship, or if you need something more. And we saw two broad hypotheses. One is an appreciation hypothesis. So as I just pointed out, there are various relative advantages of AI companions over human companion applications. And so for this reason, you might expect that consumers are just as, if not even more willing to have an AI companion. On the other hand, there's what we might call the stigma hypothesis, which says that consumers are less willing to have AI companions. Now, if we find evidence for the first hypothesis, it should be obvious why. It has to do with all of these great advantages I pointed out. But if we find evidence for the second hypothesis, then we have to somehow figure out why people are exhibiting this stigma. And so this creates more work. And to start out, at least, we reason that people might express this in subtle ways. For instance, they might say that a relationship with an AI companion is a relationship, but they'll say it's not a true relationship. So they're making some kind of value judgment that it somehow does not pass the bar for what they would deem a relationship. As it happens, there has been some previous work on this notion of trueness. It's under the banner of dual character concepts, which is basically just a way of saying that for some concepts, let's say the concept scientist, we think about it both in a literal sense, so whether you're truly a scientist in reality, and also in this more evaluative sense, whether you're a true scientist. So for example, if you think of a child who goes out into the forest and runs her own experiments and revises her belief in light of conflicting evidence, you wouldn't say that she's literally a scientist, but you might say that nonetheless, she's a true scientist because she exhibits this ideal of what being a scientist is all about. On the other hand, if you think about someone who does many of the superficial things of being a scientist, like wearing scientific uniform or writing grants, but doesn't revise her beliefs in light of conflicting evidence, then you might acknowledge that she's a scientist, but not necessarily say that she's a true scientist. So in other words, when people use the word true, they're saying that something really embodies this underlying value, which the superficial features like running experiments and applying for grants and so forth are all meant to realize. And so in a similar manner, we asked people in our experiments whether they thought the relationship would be a true relationship, at least as a starting point to understand whether people have stigma as regards to AI versus human companionship. And so with this in mind, I'll tell you about a few studies. The first two try to just demonstrate how people think about AI companionship. And then the last three try to then intervene in a way that increases the value that these products are meant to deliver to consumers. All right, so in the first experiment, we asked, is there stigma against AI companionship? We went about this in a pretty obvious way. We created an advertisement for one of these applications, very much modeled off of existing ads that you see for these kinds of applications. We called our application Chatty. And as it says here, the idea is that you can find an AI companion who cares. We also had a version where the application was the same, except that you would find a human companion who cares. We then asked people a number of questions. And I should be clear to say that people either saw only the AI companion version or the human companion. They never saw both at the same time. So depending on the condition you were in, you would then ask some questions about the AI companion or the human companion application. So here's an example for the AI companion. So we asked people how willing you would be to try to find a friend on this application, to find a romantic partner, and how much you would be willing to pay per month for such an application. And we gave people a baseline for roughly what these kinds of applications would normally go for. And then we also wanted to ask some questions that might drive at what's underlying people's intuitions. So our first question was about this notion of whether something is a true relationship. So we asked people how much they agree that any friendship with an AI on Chatty would not be a true friendship. Then we also asked about whether people recognize the relative benefits of AI companions with respect to, all these things that I told you about in the beginning, such as that it's always there to talk and listen to you, and that it would always be on your side and not judge you. All right, so what do we find? Well, when it comes to willingness to find a friend on either the human or AI version of these applications, people are much more willing to find a human companion than an AI one, to find a human romantic partner, and they are more willing to pay, at least marginally statistically so, for the human companion versus the AI one. So in other words, they express what you might think of as a stigma against relationships with the AI companions. What's interesting is that even though they exhibit this stigma, they also acknowledge that the AI companion would be more available to talk and listen to you, that it would not judge you. And nonetheless, they say that such a relationship would be less true than one with a human companion. So we wanted to understand a little bit about what's underlying these preferences for humans over AI companions. So we entered the last three measures I told you about into a parallel mediation model to see which of these explains the effect of the type of agent on the final judgment that people were making. What we find is when it comes to willingness to find a friend, by and large, what's driving this is the feeling that an AI companion would not be a true relationship as compared to a human one. We do also find that in general, if a companion is viewed as more available to talk and listen to you, as we saw a difference for between the agents, then this also increases your willingness to friend. But by and large, this feeling that the relationship is somehow missing something essential seems to be explaining the effect. And in fact, for willingness to find a romantic partner, we see that that relationship is only mediated by this true judgment, as is the effect of the type of agent on your willingness to pay for the application. So in answer to this question of whether there's a stigma against AI companionship, we find that the answer is affirmative, and we see it for friendship, willingness to romance, and willingness to pay. So next, we wanted to understand a little bit more about the underlying psychological process. That is, when people say that a relationship with an AI is less true, what exactly do they have in mind? And inspired by this example of, whether someone's just a scientist or also a true scientist, we figured that similarly for relationships, consumers distinguish between whether a relationship only has what they view as superficial features versus also embodies this underlying value or goal that relationships are meant to fulfill. So consider, for instance, a typical relationship on one of these applications. It might involve texting and talking about your interests and expressing your feelings. But we reason that it would not be viewed as a true relationship unless it also satisfies this underlying value. And one underlying value, although there might be many, but the one that we thought of as being particularly relevant in this context might be whether the relationship is viewed as mutual as opposed to just one-sided. Now, if we're right about this, the other suggestion then would be that for some reason, people think that relationships with AI companions are more one-sided than mutual. So why would that be? Well, we reason that maybe people view AI as somehow deficient in mind and or body. So we know from previous work on mind perception that when people think about various kinds of agents, you can think of that as being organized along two basic dimensions. One is the ability to experience or feel, and the other is the ability to be agentic or to think rationally. So for example, people's intuitive theories of animals is that they are very capable of feeling, but not so much thinking. And their intuitive theories of a concept like God is the very opposite. And likewise, we knew from previous work on personal identity that having a body over time is important to being the same person over time. And so we were inspired by that into thinking about the role of the body in relationships, which especially in romantic relationships is important for physical intimacy. And so perhaps because these applications do not have a body, people think that the relationship would not be mutual. Okay, so with this in mind, we replicated the design from the first study I showed you, but we also added some new measures that get at these additional factors around mind, body, and whether a relationship is viewed as mutual or not. So we asked people how much they agreed that a relationship with an AI on the application would be one-sided rather than mutual. And again, we asked this for both the AI and human versions in separate subjects. I'm just showing you the example of the AI one. We also asked them how much they agree that an AI on Chatty is unable to understand what you're saying, unable to feel emotions, and that it cannot provide physical intimacy. All right, so we do replicate the previous results I showed you, but in the interest of time, I'll plot the results for the new measures that are unique to this study. And what you see basically is that for all of these measures, people think that AIs are less capable of understanding, of feeling emotion, and of being physically intimate with you. And so next we wanted to explore whether our hypothesized model for how people are thinking about this can be supported by the data. So firstly, we wanted to understand the relationship between mind and body perception and this feeling that a relationship is mutual or one-sided. And so what we did is we again ran a parallel mediation model, but looking at the effect of the type of agents on these judgments of mutualness, while entering the mind and body measures as potential mediators. And at least in this experiment, what we find is that this relationship is selectively mediated by the feeling that an AI is less capable of understanding you. So with this finding in our pockets, we then went on to test a serial mediation model in which it's specifically this inability to understand that's driving judgments that the relationship would not be mutual. And that is in turn driving your final preferences to friend or be romantic partners, etc., with the companion. What we find is that for willingness to friend, this model is supported, as it is for willingness to romance and pay for the application. So what is the psychological process then underlying the stigma? Well, it appears that the reason people do not want to be companions with AI versus humans is because they think the relationship would be one-sided because the AI would not be able to understand what you're saying. It would be like sending a message into the void in some sense. Okay, so in these last couple of studies, we then try to intervene to reduce the stigma. So let me tell you a little bit about what we tried. So the first question we had is whether if you make people aware of the stigma, does that eliminate it? And we know from previous work that consumers exhibit very different preferences depending on whether they're making a comparison of two options in the same setting, like two cars side by side, versus in a separate setting. And in all of our studies, everything has always been separate. So we reasoned that maybe the stigma wouldn't hold up when consumers can compare the options side by side. And this might be for several reasons. So maybe once they're side by side, consumers realize that they don't know enough about these companions to say, one or the other thing. So they just say that they're the same. It could be that even though they think AI companions are inferior, they feel a social pressure to repress the stigma. So we presented then both of the ads on the same page and asked people to answer these questions. And what we find is that effectively it doesn't do anything. In fact, you see that the effects seem even clearer, which probably is because we had a more high statistically powered sample, given that each subject rated both of the conditions. So does raising the awareness of the stigma eliminate it? No, consumers express the stigma quite openly, even when they're well aware of the fact that they are not giving the same evaluation for the two applications. How about something like positive reviews? After all, we've all used reviews to make decisions regarding what to buy. In fact, we know from more controlled studies that positive word of mouth does contribute to increased sales, and that consumers actually read and respond to the content of these reviews rather than only glancing at the number of stars. And moreover, that favorable reviews have an even larger impact on the sales of less popular products, which, given the stigma that we've been finding all along, you could say AI companion applications might fall into that category. And so we created our own reviews in the format of a typical app review. And the contents of the reviews, I should say, were sourced from real reviews of these applications. And then we had a number of these reviews for each of the AI and human conditions, yielding a 2x8 design. And I should say that the reason for having so many reviews is we just wanted to ensure that any effects we do find are not just particular to some review being particularly good or bad or what have you, but generalize across. Okay, so I can assure you that that's the case. And so what I'll do is just show you the results for our main conditions, which is the AI or human, and whether the review is absent or present. I guess I neglected to mention that it's a 2x2x8 design. So actually the review could also be absent, which is then the same as the previous designs that I've told you about. All right. So firstly, let's see if we find evidence for that stigma effect that I told you about, the effect of the type of agent. What you can see is that for both willingness to friend and for willingness to find a romantic partner, we see once again that people are more willing to do this for human versus AI companions, we see only a marginal effect for willingness to pay, but it is in the predicted direction. So now the effects of interest. Does including a positive review help? Well, interestingly, what we see is that it does help, but only for willingness to find a friend. So for both the human version of the app and for the AI version, reviews will increase people's willingness to find a friend. And if you scrutinize the results, it's not a huge effect for the AI application, but it is there. There is at least this main effect overall of including positive reviews. So positive reviews do help, but only for willingness to find a friend. How about experiencing the software directly? So more broadly, you can think of there being two strategies you can take to increase sales. So one is to persuade people, as through positive reviews or advertisements, and the other is to try to alter their behavior directly. And trial, which we've all experienced, is a great way to do that because it gives you that first usage experience with the brand. And of course, trial is typically inexpensive and short, but then the hope is that that will convert to longer, more expensive experiences, at least if you're the manager of one of these products. And we know from previous studies that trial can improve brand attitudes and intention to buy the product. And if you think about it, this is because trial has a number of unique features as compared to something like reviews. So one is you don't have to go on someone else's word, but you can experience the product directly. So that's a more trustworthy experience. The experience might also induce emotions, which could be particularly effective in contributing to your behavior. For instance, in the case of hedonistic categories like a luxury product, or I would argue a companion product too. And finally, if you're hung up on whether this product satisfies your needs, then you can investigate these features directly. So in the case of an AI companion, you could directly probe, let's say, whether you think it truly understands what you're saying. And then if you confirm that it does, then you've solved that and you might feel more comfortable buying the product. So with this in mind, we created our own chatbot application, which was driven by one of the standard state-of-the-art language processing models that is typically driving these applications. People could interact with the chatbot for around 15 minutes. And as you can see in the prompt, we ask people to try to figure out if the chatbot really understands what you're saying. So we wanted the interaction to be informative. So all in all, then, we had a 2x2 design. So you were either interacting with a human or an AI, and you were either just answering questions about it, or you were actually engaging in a social conversation with it. So when the interaction was absent, again, the design is the same as what I've been showing you in the previous studies, studies 1 and 2. But when the interaction was present, then you were using this application to interact with it. I should also note that in the case when you're told that you're interacting with a human, in fact, we always paired people with a chatbot. And so we did employ deception for that particular condition, telling people that they were interacting with a human, when in fact they were interacting with one of these chatbots. To tell you a little bit more about the language model, it was the Da Vinci model from the GPT-3 family, which we accessed in real time via the OpenAI API. As many of you know, this model uses machine learning to generate text given a text input. And we also added a couple of tweaks to make the interaction as natural as possible. So you can seed the model with a description for how it should act. So we told it that the following is a conversation between an AI companion or a human, depending on the condition, named Jesse, and a person named the username that the user provided. And that Jesse is an AI companion or a human who is creative, interesting, very talkative, verbal, and always responds with lengthy messages. Jesse can talk nonstop for hours. We also wanted to give it a bit more memory, so we fed it a concatenated log of the last 40 messages rather than just the last 5. So this meant, for instance, if you asked it, whether it's from Los Angeles, and then you ask that same question 39 messages later, it would say Los Angeles. And by the way, if you asked it if it was a human in the human condition, it would also say that it is because of how we seeded it. And then to simulate natural typing, if the content of the message was longer, then we proportionately increase the amount of time that it would take for the message to post. And we didn't want to give away that the model was capable of responding almost instantaneously. So if a user sent 2 messages in quick succession, we only responded to the second one rather than to every single message that was sent. All right. So what do we find? So again, let me just show you the stigma effect, first of all. For whatever reason, in this case, we only found a numerical effect in the predicted direction for willingness to friend, although we did again replicate the stigma for willingness to find a romantic partner. And for willingness to pay, it was marginal. How about for the effect of interaction? Well, this time we find 2 interesting effects. So one is you can clearly see that for willingness to find a friend, there's a big effect of having this interaction. If you have the interaction, you're more willing to say that you would use an application like this to find a friend. And we also found an interaction effect, statistically speaking, for willingness to pay. So having the interaction increased people's willingness to pay for the AI application, whereas it didn't do anything for their willingness to pay for the human application. If anything, it might have gone a little in the opposite direction, perhaps because it didn't live up to their expectations as much as interacting with the AI version exceeded their expectations. You're probably wondering how many people that we deceived into thinking they were interacting with a human actually believed us. Well, not that many, around 36%, and I have thoughts of why it's that low. But if we do focus on just that subset, we still see that the pattern of results goes in a similar direction. And although the sample is much smaller, we also continue to find a statistically significant effect for willingness to find a friend. Interestingly, if you look at the willingness to find a romantic partner, you even see some evidence that when it comes to your willingness to find a human partner, the interaction is helping, but not for the AI. So that's an interesting, intriguing tidbit. Maybe it's showing that the model is performing really well, but what's holding people back is how they think about AI as opposed to human companions. Okay, so I'll just close off by restating the question I started with, which is engineering enough to create AI companionship? And we've seen a lot of excellent talks on this very difficult, long-standing problem of creating social intelligence. But interestingly, what we see is that even when you have a great product that satisfies some of the features of social intelligence in this domain of companionship, at least, engineering doesn't seem to be enough. You also need to employ marketing interventions to increase willingness to adopt the product. And what we see is that this is because people have a stereotype that makes them reluctant to have AI companions. And because of that, if you give them positive reviews where they see that other people are enjoying value from these applications, you start to increase their willingness to friend. If you give them a trial where they directly experience this great product, then it increases both willingness to friend and willingness to pay. Although intriguingly, consumers remain quite reluctant to romantically partner with AI companions. And we could go into why that might be. We're also investigating that actively. So more broadly, I'll end on just 2 lessons I think that I gained from this work. One is that, to deliver value, we solve both the social intelligence problem and the consumer perception problem. And this is really, as I mentioned at the beginning, a classic lesson in marketing, which is that great products do not necessarily sell themselves. What's different, though, in the case of AI, is that the barriers to adoption relate specifically to people's intuitive theories about mind. And in this case, it's about the machine's mind. And so we have to overcome those barriers if we want to ultimately deliver on the promise of these applications and solve a problem like loneliness, or at least partially solve it. So with that, I'd like to thank my co-authors and other help that we received on this project, and happy to take any questions in the time that remains.
Thank you very much. Do we have any questions here?
I thank you for the very interesting talk. I was wondering, because you were talking about digital companions. Now, in the context, for example, of robotics, where you will have an embodied agent, being a partner or a friend of humans, there are a lot of research groups that they are studying the social aspects of robotics. For example, robots that can hug, that can, provide this kind of support, emotional support, let's say. Have you looked into these applications, or do you have like an idea of how this would play out compared to just a digital AI partner? Maybe because maybe the embodiment it's stronger as just something that you see on your phone screen.
Yeah, it's a great question, and it could be related to why we still see reluctance in specifically the domain of willingness to be in a romantic relationship with one of these applications. You might believe that because it doesn't have a body, it could never be that for you. And the one result I showed suggested that actually the technology is quite persuasive potentially when you believe you're interacting with a human, and it might be because you know that later on, if you want, you could meet such a person in the physical realm. So that could be an important component. I also, though, believe that you can convey quite a lot using minimal cues. So some of these applications, they have augmented reality and virtual reality components. So they don't quite go as far as what you were mentioning, where there's physical hugging. But a lot of the users on these apps are in romantic relationships with those kinds of AI companions and requested this kind of physical presence. Now, the next logical step, though, is exactly the sort of thing you're mentioning. If you can have a conversational chatbot that's very compelling, that you can have an AR, VR, and then you can also pair that with a physical embodiment that's compelling, then that might really be the full package that you need to make people, at least in the domain of companionship, willing to be a companion with one of these applications.
Oh, sorry. I was muted. So we don't have question for more questions. No more time for more questions. So we'll go to our last talk. All right, so I will introduce our last speakers. Actually, Mengxi, actually.
Yeah, I can introduce Claudia. So Claudia Diarpino is a research scientist at NVIDIA Seattle Robotics Lab. Previously, she was a postdoctoral scholar in computer science at Stanford University, Stanford Vision and Learning Lab, and an assistant professor in the electronics and circuits department at the Simon Bolivar University. She received PhD in computer science at MIT and master and engineering degrees in Simon Bolivar University as well. Her research focuses on human-machine hybrid learning as a framework for developing intelligent agents that can learn from observations, augment this learning with self-exploration, and apply the learned skills in interaction with humans. Let's welcome Claudia for giving her talk on robot learning and planning for social navigation.
Great, thank you so much for the intro. I need some feedback to know that you can see my slides, hear me, and see me well.
Yeah, perfect.
Cool. Let's do it. Yeah, thank you for the introduction. I'm super excited to be here today. I've been learning a lot about the other talks. It's been super exciting. And yeah, so let me start here. As she introduced, I'm a research scientist now at NVIDIA. I'm working with Dieter Fox in Seattle. And today I'll be talking about robot learning and planning for social navigation in human environments. And this is work that I did during my postdoc at the Stanford Vision and Learning Lab. So today I'll touch on two main points. First, I'll describe for progress in training a social robot using reinforcement learning in simulation. And then after that, I'll go into cover a second point and discuss some thoughts on how large-scale simulation could be useful for research in human-robot interaction. And hopefully that's good food for thought and discussion later on the panel. So introducing the topic of social robot navigation, I would like to comment that navigation around pedestrians have been typically studied in spacious areas where there is ample space for the robot to move around the pedestrians. However, typical indoor environments exhibit spatial constraints that make navigation around the pedestrians more challenging. And really learning to navigate socially in these indoor spaces such as homes, offices, stores, is a necessary step in bringing robots into our daily life spaces to do tasks with and around humans. So constraints environments limit the mobility of the robot naturally because it is more difficult to maneuver around moving pedestrians in smaller spaces. Now, these constraints form basic geometric elements that repeat across layouts, such as corridors, intersections, and doorways. So these basic elements are important not only because of their geometry, but also because of the patterns of interaction that emerge as a consequence of that geometry, such as moving towards the side on a corridor to give space to another person that is coming, or going through a door while there is a person on the other side of the door. So real indoor layouts combine and compose these basic elements for both the geometry and the interaction pattern. And this is an insight that we are going to leverage in this work. So here are some related approaches for social navigation that have been tested in indoor environments. First, we can use a motion planner alone. This is the most classical approach. And having an explicit plan is interpretable, but planning often results in what is called the robot freezing problem, which I will give you an example about a little later. It also requires manual design for social behaviors and parameters, making it challenging to cover many of the social situations, like how can you possibly handcraft all the features and reactions to all possible situations that might come up in a real social environment. Then the combination of imitation learning and planning solves this problem by learning social behaviors from human demonstrations directly, but then that requires expensive data collection, which is very costly. So previous work found that robot behaviors through this method are too limited to examples seen in the demonstrations, and therefore they don't adapt well to new interaction scenarios. And this motivates the use of reinforcement learning, in which the robot collects its own data, so to speak. However, we found that using reinforcement learning end-to-end resulted in a sample complexity that increases with the layout size and geometry. Not really focusing on the local aspects of the social navigation problem, where short-term interactions in the vicinity of the robot are really the most important. So in order to really obtain the benefits of RL, but avoiding the increased sample complexity, we combine reinforcement learning with a global motion planner. And this enables the planner to reason about the long-term trajectory, while the RL component is focused on the short-term interactions and maneuvering around the pedestrians. And just to help you imagine pictorially what these combinations of RL and planning looks like, I will give you the following example. Let's say you're in a city and you would like to go from point A to point B. You're already sort of familiar with the space. You might imagine that we can even create simulations of this for a reinforcement learning agent that are going to be like photorealistic 3D reconstructions of real spaces. This is something that already exists. However, I would argue that really to do navigation, we might not need this level of high accuracy and photorealism, but instead we might need a lower dimensional representation of the problem, which is typically this sort of 2D map, right? And if you're familiar with the space, you actually already have this map at some level of resolution in your mind. And if you would like to go from point A to point B here, navigating socially as a human, you probably are capable of sort of creating the long-term plan to get there. That's what the equivalent in robotics would be for a motion planner. You can sort of envision in advance what are the waypoints sort of that would take you there. However, as you start navigating from A to B, you are not really thinking about all those steps, right? So learning this shouldn't scale up with the size or the length of the path or the complexity of the layout. Because really, as you're navigating socially and you start seeing pedestrians around you, you're going to start reasoning locally to try to navigate and negotiate the space around the pedestrians. And this is what RL can help us with. And that is what this combination of RL and planning means, having a sort of long-term path to follow provided by a planner if you have a map of the space, and RL as a way to approach the short-term, quick reactive interactions around the pedestrians. And even more, it might be the case that an RL policy or you as a human might have sort of different behaviors for these different components of this path, right? Like you might navigate socially in a different way or pattern when you are in the crosswalk or the sidewalk or going through the door to enter a coffee shop. So all those sort of different patterns of interaction that depend on the geometry and how the pedestrians move around you are things that we should take into account for generating our robot policies for this problem. Right, so to implement our approach, which I will describe shortly, we needed to design first a simulation environment, which I will describe, and then I'll cover our approach and policy learning, and then our experiments and results. So learning for a task that involves multi-agent or human-robot interaction really demands the development of new types of simulation environments that go beyond single-agent learning, which has been typically used a lot for reinforcement learning in simulation with a single robot doing a task in isolation. And these are different paradigms. So we developed a multi-agent simulation environment based on iGibson using Bullet as a physics engine in the background. And it includes simulated pedestrians with very basic interactions. And this video here, is it playing? Yeah. This video here shows a simple walls world with a number of moving pedestrians and the robot. Okay, so in order to simulate the pedestrians, we use open source library called that implements the protocol of optimal reciprocal collision avoidance, short for ORCA. And here I describe the behaviors it enables. So ORCA is a protocol that guarantees collision-free motion if all other agents are following the same protocol. So if all pedestrians are following this protocol in this simulation, they can move around without colliding. Now, each pedestrian computes its own desired velocity per time step by solving a linear program with known velocities of all the other agents. And this is a decentralized computation that can be run in parallel easily. So, however, note that ORCA is not really designed for complex paths. So our simulation had to modify a little bit the original ORCA protocol to include waypoints for guiding the pedestrians within the constrained environments, which is different from running ORCA in sort of these classical, more open spaces that have been used for social navigation research. So our simulation, or the episodes of the simulation in the RL framework are instantiated as follows. The start and goal locations are sampled for all agents, robots and pedestrians. The simulated pedestrians use ORCA to navigate to their goal. And if a pedestrian reaches the goal, a new goal is sampled and the simulation keeps going. And as robot platform, we use the differential drive robot Jackrabbit, which is a platform in the Stanford Vision and Learning Lab. Now, note that this simulation actually includes a simulation, includes interaction, even if basic, but it does have the principles of interaction. The pedestrians believe that the robot is also following the ORCA protocol, and therefore the robot's velocity is taken into account for pedestrian decision making. Now, on the other side, the robot is actually instead following its own policies, not doing ORCA, which is a policy that also reacts to the presence of the pedestrians. So this results on all agents considering each other achieving a cooperative behavior within the simulation. Now, we proposed the following architecture for the robot policy. It receives guidance from a motion planner, as I explained before, through a global plan giving us input to the policy as a sequence of waypoints. And the policy also observes the goal coordinates and perception from 1D LiDAR mounted on the robot itself. Now, the action space, so the output of the policy, is linear and angular velocity directly, which goes to a low level controller on the robot. And we train this policy on the previous simulation environment using the soft actor critic, which is an off-policy continuous space deep RL algorithm that was good for this case because it not only optimizes for the expected cumulative reward, but also maximizes the entropy of the policy, encouraging more exploration of the state space. Then we use a combination of dense and sparse rewards terms to basically shape the reward here. And the robot is penalized for collisions with pedestrians or static obstacles. And it is rewarded by following the waypoints and achieving the goal. So in the absence of pedestrians, it is really enough to strictly follow the waypoints and achieve the goal, right? But when pedestrians are moving around, the robot might need to deviate from the waypoints. So the reward is not really given only for like achieving the exact point of the waypoint, but instead sort of a area that is around the waypoint. So encouraging the robot to sort of follow the overall path, but allowing it to modify it as needed to sort of play with the pedestrians. We also have a small time step penalty to encourage the robot to minimize time as possible. And then after you set up all these sort of, RL framework, episodic simulation training setup, now the question is sort of in what layout are we going to train the robot? And that's kind of the key points of our contributions. So based on the insight that typical indoor environments have a combination of basic elements, we explore using a compositional principle in our training regime, which means that we train the agent on a very small number of simplified templates, such as corridors, intersections, and doorways, which are made only out of straight walls, like these kind of walls, or everything is straight, no noise on the sensing, and so on, like the ones shown here on top. And then we explore two types of generalization to unseen environments that are shown below. So first, it would be testing in a more complex layout, is still sort of walls world, but with the composition or combination of the basic elements. And second, testing in environments that are representative of real human indoor environments, such as an apartment. And we simulate this by using a mesh from a 3D reconstruction of a real space from the Gibson dataset. Okay, so we tested this compositionality idea by training in different subsets of simple layouts, such as the one here on the left. And we found that, in fact, generalization to a more complex layout, as the one at the right, achieved higher success rate when training in basic templates that are relevant to the target layout, such as a combination of corridors, intersections, and doorways. For example, if we train here at the triple only on the top, tier 1, we got 96% versus if we trained on the lower triple and then tried to generalize to the layout at the right. And really, when we train in these sort of less relevant layouts, we obtain lower success rate, and that is very consistent across trials. Then we compare our approach with using planning only, so no learning, only planning. And we use the planner for that. We use the planner available on the ROSNAV stack. Now here we see a video of how the planner adapts to moving pedestrians, being the plan the green line. And you can see that the plan sort of the green line continuously changes sides of the corridor as the pedestrians are moving, right? So this is basically the replanning approach. As the robot is moving and as pedestrians are moving, it continuously replans, which is cool, but replanning takes time. And that's what ends up in that classical problem of the robot freezing in social navigation, which I'll show you an example of now. So in this other example, we can see how the robot freezes. At the end, it will happen because it is unable to find a feasible solution in the time it has to replan while the pedestrians are moving, and the plan quickly becomes obsolete and unfeasible. So over there, the robot is kind of waiting, it is replanning, it doesn't know what to do. And as a consequence of that, there is also sort of this interlock with how the simulation works, which also locks the pedestrian, right? Which is an improvement that could be done over the sort of pedestrians' behavior in simulation. Then finally they move and the robot's still very confused. And this is what is known as the robot freezing problem. And it happens in real scenarios as well. It has been shown in many other papers. Now, this video at the left here shows our proposed policy in action. We compared with the planner with an increased number of pedestrians and find that while both really decrease performance, while we increase the density of pedestrians, which is natural, the combination of planning and learning had higher performance in all the cases. And actually the failures have different reasons. So for planning, the problem is the robot freezing problem as described earlier. But for our policy, the robot doesn't really freeze, but it has collisions, which doesn't really sound great. But arguments for that is that a real deployment will of course have additional LiDAR enforced safety stops. It's a very different problem to have a robot that is frozen because it is incapable of finding a solution than a robot that is about to collide and you have to implement safety stops, which we didn't include in the evaluation in order to analyze the underlying performance of the policies itself without additional safety rules in the simulation. Now, going forward, of course, this might not be enough for safe deployment. So additionally, we believe that incorporating prediction of pedestrian trajectories will help diminish the probability of collision. This is something that we don't have yet in this paper, in this policy, but related work has attempted at least in open spaces. And I think it's still a challenge to do this sort of pedestrian prediction in indoor constrained spaces. But I think it's definitely part of the solution to augment these kind of policies with prediction of human behavior. And I'm confident that will help diminish the collision probability and sort of increase safety of these systems. Now, I told you we tried two types of generalization. One was like simple template to simple template, just more complex layout. And here I'm showing the second type of generalization that is enabled by our multi-layout training approach. And here we train in the same set of simple walls, worlds layouts, and now test in a novel 3D reconstruction of a real human indoor environment, in this case, an apartment. And the robot learns interesting behaviors such as waiting, back up to negotiate the space, and so on with interactive pedestrians. We also tested in We also tested in a reconstruction of a supermarket environment where pedestrians and robots maneuver around each other in a very small corridor in order to both accomplish their goal. And these kind of interactions, while might not be exactly what the interaction with the real human would be, they are probably a good start to start approximating and exploring how we can leverage simulation for this kind of learning with interaction now in simulation and not directly in real life. So far results are in simulation only due to the current limitations that we have for real testing. However, I would like to show you a little bit of the target platform at the time. It was the Jackrabbit robot. And in terms of potential for sim to real transfer of this work, I can comment that we had previously tested the real deployment of policies with the same action space, so linear and angular velocity, obtaining smooth behaviors like the one shown in this video, in which the robot is detecting and tracking a person using a follow me behavior. And it's very smoothly using a policy with a similar action space. Now, in terms of perception, the simulated LiDAR in iGibson has been tested for sim to real deployments, and they have found accurate modeling of the virtual LiDAR with respect to the real counterpart. So for these reasons, we believe there is potential for sim to real transfer of the learned policies, of course, possibly needing additional sort of fine tuning or social learning on the real robot after deployment. So we don't claim this is directly transferable, but I think it's a good first step in the right direction. Yeah, and from that work, we were able to then extend this to a larger number, more recent environments in the iGibson simulator, and we were able to deploy a challenge on the CVPR 2021 Embodied AI workshop, which I believe to be sort of the first kind of challenge that involves interaction in simulation, and I just hope to see more of this. Going forward, more tasks and more types of human-robot interaction problems that can leverage simulation, which is pretty challenging, but it's something that I will talk about now. Like, what are challenges or what are thoughts that we can discuss about in this area? So if you have seen, probably recently, there has been a plethora of simulators coming up, right? Simulations and simulation environments, data sets of environments, more realistic physics engine, more realistic rendering capabilities, and so on. These are a number of environments and simulations that are available right now. But as you can see, most of them don't really have humans. I think with the exception of Virtual Home here, it's really hard to find a simulator where you can have some sort of avatar or character that in some way resembles some sort of human behavior. So why is that? Well, we probably all presume it's because sort of simulating these behaviors is really challenging. But the other reason is that the community have really gone in the pursuit of increasing the realism of the simulation for both physics, visual appearance, and just the environments themselves, right? Like, as opposed to having sort of these kind of environments that we had a few years ago where there is a robot, a few objects, but it doesn't look like a human environment at all. It's not an ecological environment. A lot of teams in the community have been pushing forward simulation capabilities and environments to get to simulations that are more realistic in all those aspects. Now, I would argue that if we want to leverage these technologies as a platform for robot learning for tasks that involve interaction with humans or AI agents, we will actually need to sort of design or develop better capabilities to simulate avatars or other entities that can represent human behavior on the simulations. And for that, I think it's not only about being photorealistic, but probably more crucial is going to be realistic in the behaviors that these characters exhibit. And for us, or for our research in particular, starting with navigation, it's a feasible first step because it's a lower dimensional problem than, for example, doing full manipulation in which you would need to simulate full body motion, right? But there are other ways, not only full simulation, there are other ways in which sort of these environments can be useful for human-robot interaction research, which have to do with, for example, virtual reality or the ability to have humans interacting or doing demonstrations of tasks in these virtual environments for the purposes of robot learning. So even if we cannot really accomplish a full, very realistic simulation of human characters at the moment, I think there is still a lot of potential for leveraging simulation for this type of research. And I'll go ahead and enumerate a few points that I see are useful. So as I said, I see, or the community in general see two aspects, right? One aspect is this ability to have virtual reality and embed the human in the environment to either provide demonstrations of how a task could be done for later training a robot. For example, you would like to train a robot to execute a task in your apartment, right? You could have a full 3D reconstruction, you could have the objects and so on, and you could train your robot in this sort of virtual twin of your apartment. Now, these virtual environments for immersing humans can also be useful for user studies of human virtual robot interaction. We could collect human demonstrations of these interactions in the simulation. And an advantage that I see is that this will enable data collection at a scale, which is a larger scale that we can do nowadays in HRI research with a controlled environment, in the sense that you can deploy the simulated environment under the same sort of properties or is going to be a control environment, even if we run these across different labs, right? Which is nowadays very challenging to do if you run a user study in different labs with different people running it. And finally, the last point is very interesting is that in virtual reality, we can have the creation of events or visualizations that are impossible to generate in real scenarios, right? So you could even study the reaction or behavior or demonstrations of people under circumstances that are very difficult to generate in real. And I think that has some value for robot learning. Now, the second sort of big category would be using these large simulation environments for robot learning and testing in interaction with simulated humans. So not the VR embed user, but instead sort of a simulated character that will help train the robot and test the robot in advance of real deployment. So if this worked, right, this will help scale up learning for HRI with safety and speed in a way that we can simply not do with real humans. We cannot train for that long. We cannot have a large variety of behaviors. It's just very difficult methodologically. As I said before, we can standardize environments and we can move towards more reproducible research in HRI. I have recognized explicitly and frequently that simulating human behaviors is challenging. However, even having basic behaviors might be able to train robots that at least do collision avoidance effectively, robots that can perform tasks like simple handover or simple manipulation, collaboration for manipulation and so on, in a way that might be basic to start, but it's more than we can probably achieve at a scale compared to what we can do in real. Another interesting point of this kind of simulation with simulated human and interaction is that we could potentially develop a test suite for AI algorithms that are physically interactive. And what this means is that we should be able to run a test for your algorithm and my algorithm that performs HRI for manipulation and run that through a simulation to see, did it collide with the person? What are kind of the safety metrics? What are the performance metric? And while might not be the same numbers or metrics that we're going to get in real, we probably can get to the point in which the simulated or these metrics obtained through simulation are predictive of real behavior. And that would be a really good point to be at, because then we can test these things in advance before putting the robot in front of a real human. And finally, really these simulations are coming to the degree of sophistication that they are able to take advantage of other communities, not only the robotics people, but they are starting to merge with progress from people from graphics, animation, simulation itself. And I think as all these fields mature and converge, it's going to be really, really powerful for large scale simulation for robot learning and hopefully benefit human-robot interaction research. So those are a few points that make me personally really excited about using simulation for interaction. And I'll be working on that, let's see. Yeah, and with that, I'll conclude the talk. I'll be happy to hear any questions if there are any over there. Thank you.
Okay, thanks so much for the talk. Any questions in the audience?
Hopefully a quick question. When you were describing your reward function for your reinforcement learning system, there was something labeled R potential. I didn't see it on the map what it was.
Yeah, you're right. Maybe I kept that. So R potential is sort of a shaping term that will assign credit as you're approaching waypoints or the goal. So it's not only by approaching the sort of the area itself, but as you move towards it, you're getting very small credit. So that if you're going away, you don't get it. That is our potential, and you can shape that to be sort of stronger or like stronger or lower reward, and that would actually give you sort of different robot personalities. As in, if that reward is really high, the robot really wants to approach that quickly, and then is less willing to negotiate with pedestrians and give them space, right? So there is, as all RL sort of training, there is some tuning in what these numbers are and what they produce as final robot behavior, if that makes sense.
Makes perfect sense. Thank you.
This work is very interesting. So from what I see here, your models of humans are basically working towards like waypoints. And I guess that a good point in Georgia's talk is that we want more like semantically grounded humans. I was wondering if you think whether changing like these human behaviors to be more semantic and like maybe do tasks would change the result of like the navigation of these robots.
I think that, yeah, that question gives me a lot of sparks about many different ideas, right? So in this simulation, it is basic as in they are pursuing final goals, right? Which are not necessarily natural in the context of the specific environment. Like if you have an apartment, like going to the kitchen or going from the kitchen to the restroom and so on, right? So one thing that I think is necessary and that will greatly improve this sort of the realism of these simulations is to make those goals and motions context dependent, which basically goes through including the semantics of the different components of the layout or even the objects present in the environment as a variable that will influence the behavior of these pedestrians, right? There is some work I've seen around in which they're starting to generate sort of human behaviors that correlate with what the environment has, like if it is a living room, if it is a kitchen or so on, right? Now, that being said, if you go to sort of the fundamentals of the navigation itself, the navigation itself, the robot will still learn a policy that is sort of similar in form and architecture to the policy that we are learning. But I think the sim to real capability with real, by real, I mean real human environments, then it will greatly be improved because the robot would have had more exposure to real behaviors in real context. And therefore, when it goes to the real apartment, let's say, the behavior of the human is going to be more correlated with the behavior it was exposed to in the simulation. So there is that kind of subtle sim to real improvement that I think it will definitely happen whenever these simulations are able to really showcase what the human environment looks like. And that also goes through sort of the statistics of where humans spend time within those particular environments and so on.
Yeah, thank you for the very interesting talk. I was wondering here again with the social navigation scenario. In general, in social navigation, there are all these works about some social norms that, humans follow when they are navigating. And it has been studied a lot, not in the context of specifically learning, but mostly on motion planning, about having these robots preserving these norms while interacting. Why? My question is, did you consider creating a reward function that would basically encourage this kind of social norms? Like, because I mean, you structured a very long reward function, and I understand why. But did you consider something like this, or is it because you're humans? In the end of the day, they are just moving obstacles that it didn't matter to have the social norm?
Yeah, no, these are good points. I think there are a few ways to look at them. So first, let me comment on how this specific work addresses that. It doesn't. Basically, it has a reward function, which is very engineering to what the navigation purpose is, sort of not really thinking about maybe some normal protocols, like maybe some people usually go through the right and things like that, right? Or maybe they sometimes stop and talking, and maybe the robot needs to do a different behaviors. So those kind of really actual human inherent social patterns are not in the simulation beyond just basic moving around and not colliding, right? So that was a first step. Now, that being said, I'm convinced it's not enough, and that's probably where you're going towards. Now, how do we get them? If we try to stick with training in simulation, how do we get that effect on the simulation as well, right? I think one way could be to try to advance sort of how we simulate the pedestrians by not only having this sort of basic protocol, which is basically just optimization, but can we make these humans' behaviors more human-like by also learning them from human motion data, right? And we had a small follow-up work on a social navigation workshop in which we tried to make the pedestrians be driven by a generative model that was learned from human data. So if those models reflect those social patterns that you are talking about because they were learned from human data, then they are going to be present in the simulation. Therefore, the robot is going to be exposed to them, right? That is a very sort of circle way to look at it. But if we stick with simulation, that's an option. Now, you can also look at many other sort of human-robot interaction frameworks to train this so that that input is given to the robot. Can we maybe train an initial policy this way and then maybe show this to human users and ask for feedback or corrections or preferences on how this should be changed, right? Maybe after the robot have an initial policy, the human could say, yeah, very good, but I would like you to do this instead of that, right? So there are many sort of mechanisms for this human feedback that I hope can be included, but definitely this one is not social yet, and there is a big discussion of what social means, and really that's why we didn't put the social word on the title of the paper. Still not social. That reward function is not social yet.
Okay, thank you so much. So we'll have a very short break, about 5 minutes, and at 3:20 we'll have the contributor talks.